Welcome to Module 7, Copper Cable Performance and Certification Testing. Once again, I'm Ted Chandler, your CIS instructor for this online course on network cabling systems. In this module, you will learn to first identify the various electrical characteristics that affect copper cable performance. You'll also be able to describe the tests that must be conducted to certify that the cabling system conforms to the TIA-EIA 568B.2 standard. And finally, you will learn to identify the horizontal cabling link versus the horizontal cabling channel for purposes of certification testing. This slide presents what needs to be done in a worst-case scenario. That is, in an Ethernet 1000 base T or gigabit network. In other words, this slide illustrates the transmission of electrical signals from a transmitter to a receiver or a computer gigabit NIC to a gigabit switch port and vice versa, or signal transmission from a gigabit switch port to a gigabit NIC. Remember that signals are transmitted in both directions, from the NIC to the switch port and from switch port to the NIC. Also recall that in gigabit Ethernet networks, all four wire pair are used, and the data signals are transmitted in both directions simultaneously, which is called full duplex transmission. Compare this transmission scheme with slower Ethernet networks such as 10 base T and 100 base T that use only two wire pairs and transmission in one direction, or half duplex. So the four wire pairs are stretched much more when using gigabit networks, and they are much more susceptible to performance-lowering electrical phenomena. Basically, in gigabit Ethernet networks, signals must arrive at the far end strong enough to have survived the effects of attenuation. Noise sources cannot have created confusion at the receiver. Signals sent from one end traveling over each pair must arrive at the far end roughly at the same time. And if Category 5E cable can't do it, then use Category 6. In fact, when using gigabit Ethernet, always use Category 6 cabling or optical fiber cabling. Now, electricity flowing through a cable is nothing more than electrons moving inside the cable and bumping into each other, sort of like dominoes falling. For a signal to be received properly by the receiver, enough electrons must make contact all the way through the cable from the sender to the receiver. As the frequency and consequently the potential data rate increases, a number of phenomena hinder the signal's travel through the cable and consequently the transfer of data. These phenomena are important not only to the person who has to authorize cable purchase, but also to the person who tests and certifies the cable. The current specifications for Category 5E and Category 6 copper cabling outline a number of these phenomena and the maximum or the minimum acceptable values that a cable must meet to be certified as Category 5E or Category 6 compliant. As I discussed in the previous slide, due to the complex modulation technologies used for gigabit Ethernet, the TIA has specified cabling performance specifications beyond what was included in the original testing specifications called TSB 67. The original test TSB 67 were wire map, length, attenuation, and near-end crosstalk or next. The new TIA-EIA 568B2 standards now include, in addition to the original tests, power sum and pair-to-pair crosstalk measurements, delay skew, return loss, and equal level far-end crosstalk, and even more. Some of these new performance characteristics are important as they relate to crosstalk. Now, attenuation, also called loss or insertion loss, is the weakening of a signal as it travels down the cable. Contributing characteristics to this weakening of the signal include conductor resistance, mutual capacitance, and impedance. Attenuation is measured in decibels, or dB, and I'd like you to remember just a few milestones with regard to dB. In other words, if you have a 3 dB attenuation, you have a 50% signal loss. If you have a 6 dB, then you have a 75% signal loss. 87.5 is a 9% dB loss, and a 10 dB loss is a 90% signal loss. 20 dB is 99.9, and so on and so on. So these are kind of benchmarks that you should remember, so that when you're doing the testing, you have a pretty good feel by viewing your instruments what kind of a signal loss you have. Again, let's go over that. In 3 dB signal loss or attenuation, we have a 50% signal loss. 6 dB is 75%, 9 dB is 87.5, 10 dB is 90%, 20 dB is 99.9, 30 dB is 99.99, 40 dB is 99.999%, and it goes on from there. Everything electrical in the cable isn't the signal itself. Let me back up here. Everything electrical in the cable that isn't the signal itself is noise and constitute a threat to the integrity of the signal. Many sources of noise exist from within and outside the cable. Controlling noise is a major importance to cable and connected designers, because uncontrolled noise will overwhelm the data signal and bring a network to its knees. Twisted pair cables utilize something called balanced signal transmission. The signal traveling on one conductor of a pair should have essentially the same path as the signal traveling on the opposite direction on the other conductor. As signals travel along a pair, an electrical field is created. When the two conductors are perfectly symmetrical, everything flows smoothly. However, minute changes in the diameter of the copper, the thickness of the insulating layer, or the centering of the conductor within that insulation cause disturbances in the electrical field called unbalances. Electrical unbalance means noise. Resistance unbalance occurs when the dimensions of the two conductors of the pair are not identical. Mismatched conductors, poorly manufactured conductors, or one conductor that got stretched during installation will result in resistance unbalanced. Capacitance unbalance is also related to dimensions, but to the insulation surrounding the conductor. If the insulation is thicker on one conductor than on the other, then capacitance unbalance occurs. Or if the manufacturer processes is not well controlled and the conductor is not perfectly centered, like a bullseye in the insulation, then capacitance unbalance will exist. Both these noise sources are usually kept well under control by the manufacturer and are relatively minor compared to crosstalk. You're likely to experience crosstalk on a telephone. When you hear another's conversation through the telephone, that is crosstalk. Crosstalk occurs when some of the signal being transmitted on one wire pair over to another wire pair. When a wire pair is in use, an electrical field is created. This electrical field induces voltage in adjacent pair with an accompanying transfer of signal. The more the conductors are parallel, the worse this phenomena is, and the higher the frequency, the more likely crosstalk will happen. Twisting the two conductors of a pair around each other couples the energy out of phase. That's electrical torque and cancels the electrical field. The result is reduced transfer of signal, but the twist must be symmetrical. Example, both conductors must twist around each other, not one wrapping around another that's straight, and two adjacent pairs shouldn't have the same interval of twists. Why? Because those twist points become convenient signal transfer points, sort of like stepping stone in a stream. In general, the shorter the twist intervals, the better the cancellation and the less crosstalk. That's why Category 5E and Category 6 and higher cables are characterized by their very short twist intervals. Crosstalk is measured in decibels. The higher the crosstalk values, the less crosstalk noise in the cabling. When the crosstalk is detected on the same end of the cable that generated the signal, then near-end crosstalk has occurred. Next, our near-end crosstalk is the most important within 20 to 30 meters or 60 to 90 feet of the transmitter. This slide illustrates near-end crosstalk. Crosstalk on poorly designed or poorly installed cabling is a major problem with technologies such as 10 base T, 100 base T, and especially gigabit. However, as long as the cable is installed correctly, near-end crosstalk is less of an issue when using a gigabit, because the designers implement technologies to implement near-end crosstalk cancellation. Next, cancellation techniques within gigabit are necessary because all four pair are employed for both transmitting and receiving data, as we've previously discussed. Far-end crosstalk, or fixed, is similar to next, except that it is detected at the opposite end of the wire from where the signal was sent. Due to attenuation, the signals at the far end of the transmitting wire pair are much weaker than the signals at the near end. The measurement for far-end crosstalk is used to calculate equal level far-end crosstalk, or LFEX, discussed in the next section. Most far-end crosstalk will be seen on a shorter cable than a longer cable because the signal at the receiving end will have less distance over which to attenuate. Equal level far-end crosstalk, or LFEX, is the crosstalk coupling between copper pairs measured at the point of the cable opposite to the signal source, taking into account signal loss or attenuation. LFEX is calculated, not measured, by subtracting the attenuation of the distributor pair from the far-end crosstalk on the distributed pair. The calculation describes the ratio of disturbances to the level of the desired signal. It is another indication of signal-to-loss ratio. Another way of looking at it is that the value represents the ratio between the strength of the noise due to crosstalk from the end signals compared to the strength of the received data signals. Each pair-to-pair combination is measured as the attenuation on each pair will be slightly different. If the equal level far-end crosstalk value is very high, it may indicate that either excessive attenuation has occurred or that the far-end crosstalk is higher than expected. Electrical signals through a cable at a constant speed, expressed as a percentage of light speed, called nominal velocity propagation, is propagation delay. For unshielded twisted pair cables, NVP, again nominal velocity of propagation, is usually between 60 and 90%. The manufacturer of the cable controls the NVP value because it is largely a function of the dielectric constant of the insulation material. The difference between the time at which a signal starts down a pair and the time at which it arrives on the other end is propagation delay. Delay skew is a phenomenon that occurs as a result of each set of wires being different lengths, as shown in this slide. Twisting the conductors of a pair around each other to aid in canceling crosstalk increases the actual length of the conductor relative to the cable length. Because the pairs each have a unique twist interval, the conductor lengths are unique as well. Signals transmitted on two or more slightly different lengths. Cables that are part of a Category 5, 5E, or 6 installation cannot have more than a 50 nanosecond delay skew. Return loss are signals transmitted on a pair that is both a sender and a receiver and reflected back like an echo, similar to what I'm showing here on this slide. Attenuation to crosstalk ratio, or ACR, is an indication of how much larger the received signal is when compared to the near-end crosstalk on the same pair. ACR is also sometimes referred to as the signal-to-noise ratio. It is a calculated value. You can't measure ACR, but it's calculated. Also, it's not really a ratio. It is the mathematical differences you get when you subtract the crosstalk ratio from the attenuation ratio at a given frequency. Technically, SNR also incorporates not only noise generated by the data transmission, but also outside interference. For practical purposes, the ACR and true SNR are functionally identical except in the environments with high levels of EMI, or electrical magnetic interference. Let me talk about headroom. Because ACR represents the minimum gap between attenuation and the crosstalk, the headroom represents the differences between the minimum ACR and the actual ACR performance values. Greater headroom is desirable because it provides additional performance margin that can compensate for the sins of cheap connectors or sloppy termination practices. It also results in a slight increase in the maximum bandwidth of the cable. The differential between the crosstalk noise and the attenuation loss of signal is important because it assures that the signal being sent down a wire is stronger at the receiving end than any interference that may be imposed by crosstalk or other noise. Here are all the various electrical phenomena acting on the four-pair copper cable and influencing or hindering signal transmissions. The question is, in my mind at least, it's a wonder that any signals get through unimpeded. It is very important to understand the differences between a horizontal cabling basic link and a horizontal cabling channel, especially regarding the distance limits and for purposes of certification testing. The basic link contains only the cabling found in the walls, the horizontal cabling, one transmission point, the telecommunications outlet, and one crosstalk or patch panel. It is assumed to be the permanent portion of the cabling infrastructure. The basic link is illustrated here. The channel link includes the basic link as well as installed equipment patch cords and the cross-connect jumper cable. However, the channel does not include phones, PBX equipment, hubs, or network interface cards. Two possible channel link configurations are shown above. One is the channel link for a 10-base-T Ethernet workstation, and one is for a telephone. The maximum distances for a horizontal link is 90 meters, or 295 feet, and 100 meters, or 328 feet for a channel. Certification performance testing of Category 5E and Category 6 copper unshielded twisted pair cable involves sophisticated cable testing instruments to perform the following tests. First, wire map to check connections. Then length, attenuation, near-end crosstalk, propagation delay, delay skew, equal level far-end crosstalk, power sum equal level far-end crosstalk, return loss, and finally attenuation to crosstalk ratio, or ACR. In summary, we discussed that attenuation, also called loss or insertion loss, which is the weakening of a signal as it travels down the cable. For example, the signal transmitted from the computer's NIC starts out at 4 volts but ends up at the hub at 1 volt. So the attenuation, which again is the loss of signal strength, is 3 volts or 75% or 6 dB. The near-end crosstalk is an important measurement, and it's a measure of noise coupling from the transmitted wire pair into the receiver wire pair detected at the transmitted wire pair end. Finally, attenuation to crosstalk ratio, or ACR, also known as headroom, is the difference between attenuation and near-end crosstalk. ACR is the best measurement of performance capability in copper cabling systems. We also discussed far-end crosstalk, power sum near-end crosstalk, power sum far-end crosstalk, propagation delay, delay skew, and return loss. This completes Module 7. Please take Exam 7, and I'll see you in Module 8.